On the internet, we have billions of web pages. It's impossible to manually keep track of the sites available. How can we locate information out of this massive amount of pages? Search engines are systems designed to retrieve information of a collection of documents using search queries. A search query is composed of keywords joined by logical operators. This collection isn't immutable. The internet is in constant growth. New sites are made public every day. How can we look up for new sites? Imagine that the internet is like a spider web. Every vertex is a web page, and the edges are the links between pages. So the crawler would be a spider that randomly roams the net, going from page to page, gathering its content. What it sees is the web page source. It looks for the metadata and searches for new links. In some searches, we can find millions of related results. So how do we know which results should be on the first page? We need to rank the results that most relate to the query. One way is the term frequency inverse document frequency, or TF-IDF. It calculates the relevance of a keyword has to a document in a collection based on the frequency that the word appears on the document and how infrequently it is on the corpus. That is, a document has a better score if it contains more important words. You can see more about TF-IDF in the video linked in the card. Another way, and the focus of this video, is Google's PageRank. Think of it as a popularity contest. Each participant votes for who they like the most. The person who gets the most votes wins. If you can't decide on one candidate, you can vote for a tie of two or more, but the weight of your vote will be split equally. In this example, the candidates represent the web pages, and the votes represent the links. Having that in mind, you can draw the pages and links as a directed graph. Let's have a look at the random surfer model. First, we randomly select a page to start with. Then, for every step, we randomly choose a link to follow, until there is no more page to visit. Finally, we count how many times a page was visited and what percent of the total times the surfer visits a page. What if there is a loop of pages? The surfer would wander indefinitely between pages, acting as a rank sink. We can solve this problem by introducing a damping factor, usually defined as 0.85. The damping factor means that 85% of the time the surfer will follow a link. That is, there is a 15% chance the surfer will reset to another page. Now, let's see the iterative model. The PageRank is calculated by the following equation, where D is the damping factor, N is the number of pages, M is the set containing all pages linking to page I, and L is the number of outbound links on page J. In this example, we have a directed graph, represented by the matrix pages. First, we set the initial value of every page as 1 over n. The M function gets the indexes of the ones in the column specified. The PageRank function implements the previous equation. Then we iterate over the PageRank function with enough iterations, the value converges. The equation can be rewritten in matrix notation as follows, where M is weighted directed graph and the bold one is a vector of length n containing only ones. Look at the Python code written with the matrix notation. The add operator was used for matrix multiplication. With the iteration tending to infinity, we can solve the previous equation this way, where I is the identity matrix. And this is how we implement it in Python. The PageRank algorithm presented today is the early version used by Google. Today, it takes into account several other factors to determine what pages have more relevance. The links are in the description. Thanks for watching. See you next time.